To build a Google-scale distributed web crawler from first principles, we are going to conduct a ground-up architecture review. At its core, the mechanical pipeline is straightforward. We fetch web pages, parse HTML, deduplicate content, extract links, and filter out junk. Looking at the URL frontier, this pipeline executes a breadth-first search, or BFS, graph traversal, operating on a flat first-in, first-out queue. You might wonder why we don't use depth-first search. DFS plunges deep into subdirectories, which on the web often leads to endless rabbit holes that yield no new, meaningful information. While this naive BFS pipeline looks perfect on a whiteboard, pointing this untreated architecture at the open internet will immediately result in system failure. The actual web is not a clean matrix. It is a highly clustered, chaotic, and actively hostile environment. This diagram illustrates our first critical failure mode. When extracting links, most of them point right back to the same host. Because a standard BFS processes them sequentially, our worker threads will hammer a single domain, accidentally launching a DDoS attack against it. The second failure involves ingestion. A flat queue treats every URL with equal weight, meaning the system will rank a random spam form comment identically to a massive corporate homepage. The flat FIFO queue has to go. We must tear it out and replace it with an opinionated scheduling system. A production crawler is required to actively defend against the structural reality of the web to survive, rather than simply traversing a theoretical graph. We redesigned the URL frontier by discarding the single queue concept and splitting it into two distinct tiers, front priority lanes and back host queues. The back host queues handle politeness. This is the strict engineering requirement to enforce time delays between concurrent requests to the same external server. This mapping table shows how the back queue router physically separates URLs. Specific host domains are strictly bound to isolated backend queues, ensuring every individual host gets its own dedicated lane. We then use a queue selector to map exactly one worker thread to one queue. This guarantees that the politeness delay is respected before the thread moves to the next link. Upstream of those politeness queues, we tackle priority. We install a prioritizer module at the top-level front queues to evaluate incoming URLs using a scoring algorithm. URLs are scored based on business value metrics, typically factoring in page rank, overall website traffic, and update frequency. When selecting from these priority queues, we apply a mathematical bias. High-priority queues are chosen aggressively, but we maintain a steady trickle of low-priority selection to prevent the bottom-tier queues from completely starving. To keep the index current, we implement a recrawl freshness timer. High-value targets are looped back into the queues frequently, while stagnant pages decay into longer intervals. By separating these layers, the URL frontier completely decouples the business priority of a link from the physical politeness constraints of the target server. Once a URL clears the scheduling tier, we move downstream to the exact moment before it is handed to the HTML downloader. This text file is a site's robots.txt. It acts as a mandatory rulebook checked before a host is crawled. Notice the disallowed text blocks, demonstrating how domains enforce rigid rules on what paths our crawler can access. Fetching this rulebook over the network for every single request would paralyze the system. Instead, we install a heavy caching layer to store rules locally. To achieve necessary throughput, we distribute our crawl jobs across geographically dispersed servers, partitioning the entire URL space using consistent hashing. Yet, even with multiple servers, we hit a silent killer of performance: synchronous DNS resolution. Converting a URL to an IP address holds a worker thread hostage for 200 milliseconds. The engineering fix is intercepting requests with a local DNS cache. Scaling a web crawler requires ruthlessly eliminating the synchronous wait times of the open internet, rather than simply adding more hardware. When operating a distributed system at this massive global scale, you are essentially guaranteeing the statistical certainty of continuous hardware failure. Our crash recovery protocol relies on hybrid memory disk buffers. This setup persistently saves the frontier state without bottlenecking input and output speeds. We also build a modular parsing architecture. If we need to support new formats like image files or dynamically rendered JavaScript in the future, engineers can swap in new extraction rules without rebuilding the core. On the open web, we frequently encounter the spider trap, an infinitely repeating, dynamically generated URL path explicitly designed to capture and paralyze naive bots. We break these loops by enforcing strict max depth limits and applying aggressive path repetition filters. Before any extracted page hits storage, we integrate duplicate detection via checksums. This instantly discards scraped mirrors and infinite spam loops. To survive in production, the architecture must treat the web as an actively hostile adversary, building deep resilience against both internal crashes and external sabotage. Pulling back, we see the fully assembled production architecture: prioritizer, politeness queues, robots gate, downloader, and DNS cache functioning together. A single URL enters the frontier, gets scored, waits patiently in a host queue, clears the rules gate, and is successfully downloaded. Compare this highly opinionated, multi-layered reality to the naive, flat queue script we examined earlier. A production web crawler is not a graph traversal algorithm. It is a defensive, distributed scheduling system. Engineering at scale rarely means mathematically forcing a process. It means delicately balancing business objectives against the uncompromising physical limits of the web.